Alright, in this video we are talking about one-sided limits and two-sided limits. Now, one-sided limits can be either left-sided or right-sided limits. And whenever I say two-sided limits, this is what a lot of times for the rest of the course we're going to just refer to as limits. So if you see someone use the word limit without actually specifying right-sided limit or left-sided limit, what they mean is actually a two-sided limit. But we'll get into the details about what this means. Now, this is a really simple example of limits, but here in this box, where a function is continuous, the limit is equal to the function evaluated at that point. So, for example, suppose our function f of x, this is just the name of my function, suppose that this function is continuous at the point x equals 5. And if we evaluate my function f at the input 5, and the output of my function there is 42, so we say f of 5 equals 42, then we also know that the limit of my function f of x as x approaches 5 is 42. And this is because the function is continuous there, and we know what the function is there. And so in this case, the whole concept of a limit is really not that interesting, right? The limit of the function is just the value of the function if the function is continuous there. But we're actually going to find that limits do become actually an interesting concept to think about when we consider points where a function has a discontinuity. So it's at those discontinuities where we actually care about what the limits are. Now we've already talked about what it looks like to have a point discontinuity with this example. And we've talked about what it means to have a jump discontinuity in your function using this example. We also talked about what it means to have an essential discontinuity using this example function. And we also talked very briefly about what it means to have an oscillating discontinuity. Now, we will introduce the concept of a right-sided limit. So remember, a one-sided limit can be either right-sided or left-sided. And what we're going to use in our symbolic notation, our little math notation to represent a right-sided limit, is something like this, where I say the limit as x approaches c with a little positive sign of your function, which might be f of x or g of x or some other function name here. But what makes this right-sided is this little plus sign here. Notice the plus sign comes after the c, so we're not just saying that c is a positive number, but when the plus sign comes afterwards, that's what specifies that this limit is a right-sided limit. Now, the way that we are going to find right-sided limits, basically, we're going to start at some input that's larger than whatever that c value is, and then we're going to take steps in the left direction so that x becomes closer to c. In other words, you might say that we are approaching from the right side. Then, when we do this, the right-sided limit is the value of the function. Well, I should say, the right-sided limit is the value the function approaches as x gets very close to c. Maybe this doesn't make sense, but hopefully these examples will start to clear things up for us. Like, consider the point discontinuity example from earlier in the notes. And what we're going to do is we're going to find the following right-sided limit. So I want the right-sided limit, hence x is going to be approaching -3. So the negative sign in front of the 3 means I'm approaching x equals -3, but this positive sign after the 3 means this is a right-sided limit. So let's take the right-sided limit as x approaches -3 of our function with the point discontinuity. So here we go, and here at this point is x equals -3. And remember, I have a point discontinuity here, so that means that if I just try to evaluate f of -3, this does not exist. because that would make my denominator 0. However, what we're trying to find is the limit as x approaches -3 from the right side of my function f of x. And to do this, all I have to do is choose some value on my x-axis that's larger than -3, and then start to walk towards it. So take a few points getting closer and closer to my limit point, x equals -3, as I approach from the right side. And as I do this, we're going to notice when I evaluate my function at each of these points, the value that my function is approaching as my inputs get closer and closer to -3, while my function is approaching this value y equals -2 here. And so this limit, this right-sided limit, is -2. Okay, so that's one example of a right-sided limit we can take. So notice our function was not continuous there at x equals -3, but we could still find the right-sided limit, which was -2. Next, consider the jump discontinuity example from earlier, and we're going to find the right-sided limit of that function as x approaches -1, again from the right side. So going up to our jump discontinuity. Here, at this point, x is equal to -1, and what I'm going to do is just choose some value for x that's greater than -1, and I'm going to move closer and closer to that point x equals -1 along the output values of my function. So I'm approaching from the right in order to get the right-sided limit. And as I approach from the right, it looks like the values of my function are approaching the value +1. So we'll notice again that if I just evaluate f at the value -1, this does not exist because I can't divide by 0. And what we're trying to find now is the right-sided limit as x approaches -1 from the right side of my function f of x, and we just found this limit to be +1. Okay, move on to another example. If I want to consider the essential discontinuity example and find the limit as x approaches -2 from the right side, let's take a look at this one. So here, at this point, this is x equals -2, and what I need to do is choose a value for x that's larger than -2, and then approach that point coming in from the right side, and we'll see what value is the output of my function approaching as the input to my function approaches x equals -2 from the right side. Well, as I'm, walking along my function, approaching from the right side, it seems like it's going up and up to +infinity. So we'll notice again that if I evaluate my function at -2, it doesn't exist because I can't divide by 0. But what we're trying to do now is take the limit as x approaches -2 from the right side. And when I take this limit, what we just found is that we're actually approaching +infinity as we approach from the right side. Okay, now one final example for the right-sided limit, we'll consider that oscillating discontinuity from earlier and try to take the right-side limit in the same way. So here's my oscillating discontinuity. And what I want to do is, at this point where x is equal to 0, I know that my function here would be sine of 20 divided by 0, but since I can't divide by 0, this does not exist. So what we'll try to do here is take the limit as x approaches 0 from the right side of my function and see what happens. So starting somewhere on the right, so for some x larger than 0, I'll just, see what my function evaluates at as I get closer and closer to x equals 0. And I may have to change colors here so that you can see it. But what's happening here is I'm not actually approaching any particular value of my function. It's just kind of jumping around at random, because no matter how close I get to the point x equals 0 in the input to the function, there's always infinitely many oscillations of the value or the output of the function. And so again, this is a weird case. This is a very strange discontinuity. And so actually the right-sided limit also does not exist, because my function isn't really approaching anything. Okay. So moving on, we'll talk about left-sided limits. And I think you'll be very pleased to learn that a left-sided limit is really a lot like a right-sided limit. But our notation that we use differs, because if I want to tell you that x is approaching some number from the left side, I'm going to use a negative sign after c here, after the constant in the limit expression. So this notation here tells you we're taking a left-sided limit. And so what we're going to do is we're going to go through the point discontinuity example, the jump discontinuity example, the essential discontinuity example, and the oscillating discontinuity example. And this time we're going to take a left-sided limit as x approaches that limit point. So for the point discontinuity, notice x is going to be approaching -3 from the left side. So I have x arrow -3 negative here in this little limit expression. That's saying approach -3 from the left side. And so that's what we'll do. Taking the left side limit is x approaches -3 from the left side, taking the limit of my function. And that means I have to start from some x that's less than -3 over here on the left. And then I'm going to, be approaching x equals -3 from the left side. And so evaluating my function at each of these points, getting closer and closer to x equals -3, the value that the output of my function is approaching looks like it's approaching also y equals -2. So this would be my left-sided limit. And you may notice that for this example, the left-sided limit and the right-sided limit are the same. For my next example, let's look at the jump discontinuity. If I want to find the left-sided limit, I write lim, x approaches -1 from the left side of f of x. And this means I have to start somewhere on the left side of -1 and then take a bunch of output values from my function as my inputs are approaching x equals -1, and see that as I approach from the left side, the values of my function are approaching -1 here. So this time, it's not like the point discontinuity. This time my left-sided limit is actually different from my right-sided limit. For the essential discontinuity, we'll do the same thing. So I'm trying to take the limit as x approaches -2 from the left side of my function f of x. And starting from the left and taking steps, getting closer and closer to x equals -2 for the input to my function, we're going to evaluate my function at each of those points. And as I do this, approaching x equals -2 from the left side, it seems like the value, the output of my function is approaching, is -infinity out here. And so again, this is a case where the left-sided limit and the right-sided limit seem to disagree for the same point. And then finally, you can work through this on your own if you like, but the oscillating case isn't so important to us in business calculus. And you can probably see, based on the symmetry here, that the left-sided limit will actually be the same as the right-sided here, in that as x approaches 0 from the left-sided limit does not exist, because this is just a very strange thing going on here. Very weird function. Now, we've talked about right-sided limits. We've talked about left-sided limits. Now let's talk about two-sided limits. So, a two-sided limit exists when both the right-sided limit and left-sided limit exist and are equal. So if both of the one-sided limits exist and those one-sided limits have the same value, that's when we say that we have a two-sided limit. In some cases, the right-sided limit and left-sided limit do not agree, and in other cases, they do agree. And so we've even seen that in our examples so far. We also commonly call a two-sided limit just a limit for simplicity. And what we use, and notation-wise, to designate a two-sided limit is we just say that x approaches some number and we don't even bother with any plus or minus sign after the c, because we're talking about both the left-sided and the right-sided limit, assuming they're kind of the same thing. So going back to our examples, we'll talk about when our left-sided limits and our two-sided limit, we're talking about our two-sided limit now, and whether or not that exists. So for the two-sided limit, I write limit as x approaches -3 of my function. And in our case, the right-sided limit exists, the left-sided limit exists, and these are equal to each other. And so my two-sided limit does exist and is equal to -2. For this next example, if I'm talking about the two-sided limit, I write lim as x approaches -1 of my function. And my right-sided limit exists, my left-sided limit exists, but they aren't equal to each other. And so that means that my two-sided limit does not exist. Okay. For this essential discontinuity example, when I'm talking about the two-sided limit, I write lim as x approaches -2 of my function. And my right-sided and left-sided limits, they both exist, but they actually have different values, right? Positive infinity and negative infinity are not the same, so that means that my two-sided limit does not exist. And finally, again with the oscillating discontinuity, since the left-sided limit doesn't exist and the right-sided limit doesn't exist, then the two-sided limit also does not exist. So hopefully that clears things up about two-sided limits, or as we like to call them, limits. Finally, I'll end this video with a third definition of continuity. So we can say a function is continuous at some input where x is equal to c, just any number, any input, if and only if all of the following are true. So number one, your function f evaluated at c, that value has to exist. Your function has to be defined at that input. Number two, the limit, which is the two-sided limit as x approaches c, of your function has to exist as well. And remember, for a two-sided limit to exist, that means that the right-sided limit exists. That also implies that the left-sided limit exists. And that also implies that the right-sided limit and the left-sided limit are actually equal to each other, right? So it actually means quite a bit to say that the two-sided limit exists for a function at a point. And then the third bullet point here is saying that your two-sided limit is equal to your function evaluated at the same point. That's what it means for a function to be continuous at some specific input. Now here, in the second paragraph, we're saying a function is continuous over some interval if and only if that function is continuous at every point in the interval. Excuse me. So, if this is all true, not just for one point, but for every point in the interval, then we say the function is continuous over the interval. And then lastly, we say that a function is a continuous function if that function is continuous over its entire domain. And so hopefully this isn't, too technical. And I want you to remember that our three definitions of continuity that I've given so far in this course, they all really mean the same thing. And so if it helps, just remember the original definition of continuity, which is that if you have some function, y equals f of x, and you want to draw this function on an xy plane, as long as you can draw the entire function without lifting your pen, that means it's continuous. It's those places where you lift your pen that create a discontinuity. And this is all just us, mathematicians being especially technical and wanting to specifically define what it means to be continuous. But if that's too confusing, again, I like to remember continuity by just, can you draw the curve describing the function without lifting your pen?